one arc and the other arc on the surface.
Right, right. You have two separate copies of this while orbit in the ideal situation that don't talk to each other, basically. Yeah.
From surface to right path, linking one and the other arc to the other.
Yes, precisely. Yeah. Thank you.
So if the wild system is finite dose, so the bulk, you have a bulk system as well, right? So then once you're considering this quantum oscillation of the arc, the electron will go from firstly on the surface on the arc, then it will go to it's possible for this electron to go to the bulk Fermi surface. Then it's circling around the bulk Fermi surface, but it can circle for many times before it runs into the other surface.
Yeah, so I don't think this actually happens. So there's some topological connection between the bulk chiral Landau level and the surface arc, and the surface doesn't go into these non-chiral Landau levels, it goes straight into the bulk one. So unless you scatter, this process where you kind of circle many times.
So the point is that if it circle many times, it's very difficult to estimate how much time it spends on circling on the bulk Fermi surface.
But as I said, unless you have impurity scattering, this won't occur. You go straight through into this chiral mode instead.
Okay, if there's no more questions. Oh, there's one question back.
It kind of seemed like it was important to be able to follow the orbit of the, so you are along the arc and then you go through the bulk. So in the bulk are the bands with less well defined than they are at the surface, right?
In what sense? I mean,
well, so at the surface, I mean, it's kind of a nice picture, but you have the well-defined state, linear dispersing state. And then, at least in the pictures that you and Sid drew, you were following your surface state, which then went into the bulk and then back up into the other vial point. So when you're inside this, or you're inside, together with the other band, can you really say that you're staying on that same band?
yeah, this is this kind of topological argument that I gave. So that the bulk chiral Landau level has to be able to turn around, and the only way it can do this is through this surface arc. And so they're actually turned into this state when you turn on a magnetic field. And so you really have some well-defined connection between the surface arc and the bulk chiral Landau level, not the non-chiral one. Yeah, it's related to Chi's question. But the bulk bands are well-defined in the clean, okay, under ideal conditions in the clean states are clean enough to see bulk quantum oscillations. You have these nice separate bulk Landau levels, and they're very well-defined. Just the chiral one connects to the surface state. The other one can turn around just by scattering off the surface on their own. And you actually see exactly this if you just put this problem on a computer and find the exact eigenstates. So the semi-classic picture I gave was just the simplest way to understand it. But you can also confirm this directly numerically that this occurs.
Even with these interactions?
Yeah, so interactions are probably not very important at low temperatures because the scattering rate for these electrons will go down at some kind of chi-squared if you have some built in. So if you cool enough, I think you do. And these are weakly correlated materials, so I think you can probably ignore these phasing from interaction.
Yeah, I think we have exhausted all the questions, so let's thank the speaker again. And we will reconvene here at 11.
Okay, thank you. I'd like to first thank the organizers for having me to give this talk. And this is work that I did That one, I was at the University of Toronto with Leon Key and Eric we just saw. I'm at the University of Waterloo now. So this is about a generic spin model for the honeycomb iridates, including some effective critical distortion. So today you've heard a lot about honeycomb iridates. So I'm going to go very, very quickly through my first sort of introductory slide. So we've seen this cadet model a lot, and so I'm not going to try to convince you that it's interesting right now. And again, we know that these are built from these gay effective half states. You know, they're strongly spin orbit entangled wave functions that give rise to interesting anisotropic physics. And again, there was this lovely proposal from Shelley and Galoon where they showed that if you had edge-shared octahedron and you only had oxygen needed popping, you could generate this coupling in a real solid-state system. One thing I just want to point out for future use is that when you do this, it comes out negative. So I'm going to call this ferromagnetic coupling. And again, very, very quickly, you can, in principle, realize this type of physics in these honeycomb iridates. Sodium, iridium oxide, and lithium, the alpha lithium. Okay, I won't do that again. So we know that they're not spin lithium. Right? We know they order magnetically. There's a zigzag pattern for the sodium. And for the alpha lithium, some indications of spiral order. Again, there's no definite statement on that just yet. So what else do we know about this order? Well, you might think that if we see this thing ordered, you might have gotten spin liquid physics completely.
About K1, K2 model, frankly, it's kind of new, interesting quantum/classical model. And the reason we studied this model was motivated by experimentalists. So let me first start by acknowledging my collaborators. So this work, which I'm going to talk about, is mostly done with Ioannis Rusa-Hatzakis, who is now in University of Minnesota, and Craig Price, who is in Penn State, and some previous results were obtained with Yuri Sudov, who is my PhD student, and with Peter Wolfe, collaboration with FRG guys, Stefan Rachel, Johannes Solter, and Ronnie Tamaris, who did the FRG study of this K1, K2 model. So here is the outline of my talk. So I will start with motivations why we decided to study this model, and I will advocate also the importance of second neighbor desires interaction to resolve at least most of the puzzles connected to sodium iridates. We've heard a lot about this compound already. And then I will present and discuss this K1, K2 model. So K1 is K-type interaction on nearest neighbor, and K2 is K-type interaction on second neighbor. And then I will discuss both classical and quantum phase diagram. And I will show that this model actually has completely different quantum and thermal spin fluctuations. And basically, most of the results which I'm going to present today is in this preprint, and some final temperature properties are in preparation, so we are going to submit it soon. Okay, so I don't think that I need to go to motivation. So once again, it was the work by George and Guignard, who showed that in this family of iridates, honeycomb iridates, it can be very large K-type interaction, which come from this interplay between super exchange arising through this 90 degrees hopping. And what was also important that in these compounds, Heisenberg interaction is there because 5d orbitals of iridium atoms are rather extended. And I think the main motivation for many experimentalists was that the spin liquid phase is in fact quite stable with respect to Heisenberg perturbation, and therefore it was still a big hope to see spin liquids in this compounds. And basically, in this original model, it was a part of spin liquid phase. It was two magnetic phases, simple two sublattice antiferromagnet, main state, a small Kitaev interaction, and the stripy phase. And when people start doing experiments, especially in the sodium iridate, then they found something else. I don't need to repeat many things what just said by Radu Caldea, but let me tell what were the questions for myself, what I could not understand in this compound. So first of all, from quantum chemistry results, it was shown that Kitaev interaction is indeed the dominating interaction, it's ferromagnetic one. So basically it fits to the description of the Kitaev-Heisenberg model, and if you just take these values and plug it, you should get spin liquid, but it's not in the spin liquid state. Both sodium iridate and lithium iridate, and now there is another compound, ruthenium chloride, they all order at rather low temperature. So this is question number one. Why sodium iridate order? So second question is why Curie-Weiss temperature is large and antiferromagnetic if we see that the dominant interaction is ferromagnetic. So that was question number two. So basically the Curie-Weiss temperature which was obtained for sodium iridate was minus 125 Kelvin. So this we should understand too, I think. The third question was why it orders to zigzag phase, while in the original model this phase was not present. And basically zigzag phase, you have two bonds, you have two ferromagnetic bonds and one antiferromagnetic bond, and you can have zigzags running in three different directions. And basically it was a suggestion first coming from Itamar and also from the paper of Rado's group that it should be further neighbor interaction to explain zigzag. Question number four actually comes from very recent work by Vigekin group, and we heard about it yesterday. So it's basically that the order parameter, the spins point in the phase diagonals. While if you do some order by disorder for nearest neighbor Kitaev-Heisenberg model, then you see that both quantum and thermal fluctuations choose cubic direction. And then if you add more terms, and we heard about this by Kingat yesterday, that in principle you can do some fine-tuning and get this phase diagonal direction. But we were thinking maybe there is something else behind this suggestion. So basically I want to point that the K2 interaction, the Kitaev interaction on the second neighbors basically helps to resolve all these four questions. So what we did with Yuri and with Peter, basically we took the tight binding parameters provided by Roger Valenti group, so it's Katerina